There are an infinite number of ways to write the software for an embedded system, but which way is the right way? The number one priority will always be to write code that meets the system requirements, but how the code is written can have an immense impact on modularity, maintainability, and testability. There is a concept called tell, don't ask, or TDA for short, that has been popular for many years among object-oriented programmers. It reminds programmers that objects should be responsible for their own data. The objects should be the ones to make decisions based on that data, not the application at large. This advice applies easily to embedded programmers using C++. It's equally valuable for most of the embedded community who are using non-object-oriented languages like C. TDA comes from a book called The Pragmatic Programmer: From Journeyman to Master by Andrew Hunt and David Thomas. Published in 1999, it's one book in a series called The Pragmatic Bookshelf. It aims to provide a pragmatic collection of suggestions to improve software development. Since it was written, several concepts from the book, such as rubber duck programming and TDA, have become popular in the industry. For object-oriented programmers, TDA encourages good programming practices like encapsulation and event-driven design. In embedded systems, it encourages the programmer to decompose the system into modules that are responsible for their own data. TDA aims to take low-level decisions away from the application and give that decision-making power to the modules. This yields a number of positive effects. It makes the application simpler and easier to maintain, and the code that's written using this principle is more easily tested. To demonstrate how TDA helps simplify application-level code, consider this code that might be part of a product like a handheld medical device or portable game console, something that runs off of primary cells but has backup rechargeable batteries. This code puts the system in standby when the battery is low. In the non-TDA example, the application is responsible for knowing that the critical battery level is different when running off of AA batteries versus LiPo batteries. It's also responsible for knowing the critical threshold for each. In the TDA example, all that low-level knowledge is contained within the power subsystem. A future engineer who has to modify the application is unlikely to know or care how those values were chosen. Encapsulating that decision-making in the power subsystem makes it less likely that those values will be inadvertently modified or left out by a future maintenance effort. Another consequence of this design principle is that the system is easily exercised from the command line. The command line interface is essentially an extension of the powers granted to the application. If the application design is complex, the command line code to exercise the system will be complex. Instead of manipulating the data in modules to trigger events, events can simply be dispatched by the command line. This technique is not adequate to test modules at the function level, but it helps greatly with integration tests. This design principle lends itself well to IoT products that combine real-time data collection and an asynchronous networking module. In these products, the application usually oversees data collection at a high level, aggregates data, and transfers it to the internet or a mobile device. By decoupling the intricacies of the low-level system from the application layer, it frees the designer to focus on elegant and stable top-level design.